Hello, viewers. In today's session, we are going to discuss a very important and conceptual problem from three-dimensional geometry. And here we are going to discuss this problem where we have to find the equation of the plane which passes through these two given points, the point P minus 1 comma 1 comma 1 and the point Q 1 comma minus 1 comma 2, and the plane is perpendicular to this given plane whose equation is 2x minus y plus 2z is equal to 6, right? So here we'll see how we can find out the equation of a plane which contains these 2 points, and it is perpendicular to this given plane. So let us start. So now let us draw a rough diagram. So here the required plane may be taken like this. This is the plane whose equation is to be obtained, and here this plane may be denoted by say pi 1, and this plane pi 1 it contains these 2 points P and Q, right? And this plane pi 1 is given to be perpendicular to this plane, and let us draw this plane like this, right? So here we can denote this plane by pi 2, right? Okay, so now here we'll make use of the concept of direction cosines, right? Suppose the plane pi 1 has the normal vector like this, and let us draw this normal vector as n1. So this is the normal vector n1 to this plane pi 1, and this plane pi 2 has the normal vector like this, right? So here this plane pi 1 is perpendicular to this plane pi 2. So when two planes are perpendicular to each other, then their normal vectors are also perpendicular to each other. So pi 1 perpendicular to pi 2 implies that the normal vector n1 to this plane pi 1 is perpendicular to the normal vector n2 that is to the plane pi 2. So here this angle is 90 degrees, right? So here we'll apply the concept of direction ratios, and let us first write the equation of the plane pi 1 as a times x minus x1 plus b times y minus y1 plus c times z minus z1 is equal to 0. So this is an important concept, right? So the equation of any plane which passes through a point say x1 y1 and z1, the equation of that plane may be written like this, right? And here a b c are the direction ratios of the normal vector, and here we have assumed that the normal vector to this plane pi 1 is the vector n1. So n1 has the direction ratios as a b and c, right? So now this plane pi 1 contains this point p, right? And the plane P has the coordinates minus 1, 1 and 1. So this equation must satisfy this point, right? So taking x1, y1, z1 as minus 1, 1, 1, in this equation, the equation of the plane pi 1 may be written as a times x plus 1. Here we take x1 as minus 1, so minus and minus becomes plus, and then we have b times y minus 1, and then c times z minus 1, and this is equal to 0, right? So this is our equation number 2. So now this equation also satisfies this point, that is point q, that is 1 minus 1 and 2. So this point q also lies on this plane pi 1. So this point also satisfies this equation too. So let us write for x, y and z as 1 minus 1 and 2. So we have now the equation a times 1 plus 1. Then we have b times here we have y is equal to minus 1, and then we have c times 2 minus 1. So z is equal to 2. So now we have an equation containing a, b, c, where a, b, c are the direction ratios of the normal vector n1 to this plane pi 1. So we have now 2 times a, then we have minus 2b, and here we have simply c, right? So now we have this equation in a, b and c. Now let us form another equation in a, b, c by using the concept of direction ratios, right? Now see, the direction ratios of the normal vector n1 are a, b, c, and the direction ratios of the normal vector n2 to this plane pi 2 may be written with the help of the equation of this plane pi 2. So here the coefficients of x, y and z gives us the direction ratios of the normal vector n2. So we have the direction ratios of vector n2 as 2, minus 1 and 2. So here we have 2, here we have minus 1, and here we have 2, right? Now the plane pi 1 is perpendicular to pi 2. So the normal vector n1 is perpendicular to n2, right? So now let us apply the condition for perpendicularity of two vectors. So when two vectors are perpendicular and they have the direction ratios as a1, b1, c1 and a2, b2, c2, then the condition for perpendicularity of two vectors is given by a1 times a2 plus b1 times b2, and then we have c1 times c2 is equal to 0. So here a1, b1, c1 may be taken as a, b, c, and then a2, b2, c2 may be taken as 2, minus 1 and 2. Now applying this condition, we have a times 2, and then we have b times minus 1, and then we have c times 2, and this is equal to 0. So we can now write here 2a, then we have minus b, and then we have 2c is equal to 0. So this is our equation number 4, right? So now we have two equations in a, b and c, and now we have to solve these two equations in a, b and c. So now to solve these two equations, the usual practice is to make use of the method of uh, that is cross multiplication, right? But here we are going to use the method of elimination. So we'll select any one of these variables and we'll try to eliminate that variable from these two equations. So here we can select a as the variable to be eliminated. So let us subtract these two equations. So subtracting equation 4 from equation 3, we have here the sign minus 1, here we have plus, and then we have minus, and these two terms 2a and minus 2a get cancelled, and here we have minus 2b plus b, that is simply minus b, and c minus 2c is minus c, and we have minus b minus c equal to 0. So we can now write here minus b is equal to c, right? So now here let us introduce a scalar, say lambda, which is a real number, right? So we can take minus b is equal to c is equal to lambda. So the purpose of introducing this scalar lambda is to express a, b and c in terms of lambda. And remember here lambda is not equal to 0, that is it is a non-zero, right? So from here we can obtain minus b is equal to lambda, so that b is equal to minus lambda, and then c is equal to lambda, right? So now substituting the values of b and c in any of these two equations, we can express the value of a in terms of lambda. So let us substitute the values of b and c in equation 3. So we have now 2a, and then here we have minus 2, and b is minus lambda, then c is lambda, and we have 2a plus 2 lambda plus lambda is equal to 0. So 2a plus 3 lambda is equal to 0. So we can now write 2a is equal to minus 3 lambda. So a is equal to minus 3 lambda over 2. So now we have the values of a, b and c in terms of lambda. So now the equation of this plane pi 1 can easily be obtained by substituting the values of a, b and c in equation 2. So here we have a is minus 3 lambda over 2, and here we have x plus 1, b is minus lambda, and here we have y minus 1, and c is lambda. So we have lambda times z minus 1 is equal to 0, right? Now see here lambda appears in all these three terms, right? So if we take lambda as common, so we have minus 3 over 2. Here we have x plus 1, then we have minus y minus 1, and here we have z minus 1 is equal to 0. Now this scalar or this real number lambda is not equal to 0. So this expression has to be equal to 0. So we have minus 3 by 2 x plus 1, then we have minus y minus 1, and then we have z minus 1 is equal to 0, right? So let us now here arrange the terms by multiplying throughout by 2, so that we can easily get rid of this factor 2. So we have minus 3x plus 1, and then here we have 2 times y minus 1, and here we have 2 times z minus 1 is equal to 0. So now we have minus 3x minus 3 minus 2y plus 2, and then we have 2z minus 2 is equal to 0. So let us simplify. So we have minus 3x minus 2y, and then we have 2z, and here we have this 2 and this 2 get cancelled, and we have minus 3 is equal to 0. So now let us multiply this equation both sides by negative 1. So here we have 3x, then we have plus 2y, then we have minus 2z, and here we have plus 3 is equal to 0, right? So this is the required equation of the plane pi 1, which contains these 2 points P and Q, and this plane is perpendicular to this plane pi 2, right? And we can see that this equation is of this form, that is ax plus by plus cz plus d is equal to 0, because the equation of any plane can be expressed by this equation of this form: ax plus by plus cz plus d is equal to 0. So this is a first degree equation in x, y, and z. And a, b, c gives us the direction ratios of the normal vector to the plane pi 1. So here the coefficients of x, y, and z are 3, and then we have 2 and minus 2. So the direction ratios of the normal vector n1 are given by 3 comma minus 3 comma 2 comma minus 2.